This is lesson 5.3, Orthonormal Bases in the Gram-Schmidt process. This is our final lesson in this chapter, and we are going to end by really building on the concepts that we've been learning both in chapters 4 and 5, and talk about a very special kind of basis in a vector space, and some of the characteristics involved in what makes those bases special. But before we jump into that, let's think back for a minute to what a basis is. And we learned this back in chapter 4. A basis is basically a subset in a vector space. So in this case, if we say that it's a basis is of a vector space V, is the set of vectors S in V, whose linear combinations span V and is linearly independent. In other words, I have a vector space, and in that vector space, I have a subset of vectors whose linear combinations will create all of the other vectors in V. And there is no vector within that subspace that is a linear combination of other vectors in that subspace. That creates the linearly independent. That's a basis. So as an example, and this was kind of a common one that we saw, in R3, we could say that it has the basis. We'll call this basis B, made up of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that would be a basis in R3 because, again, every single vector in R3 can be created through a linear combination of those three vectors, and none of those three vectors is a linear combination of the other two. Okay. Now this is one that we happen to call a standard basis. And if you remember, there were both standard and non-standard bases, but this happens to be a standard basis. We're going to talk about both in this lesson. But basically when we look at this is a unique kind of a basis, because if we were to graph this basis, we would have a vector 1, 0, 0. So that'd be like right here. That goes out to a length of 1. We have 0, 1, 0. That would come off on the y-axis here. And we have 0, 0, 1. That would come up along the z-axis here. Now, one thing to note here, hopefully very obviously, is that all of these vectors have a magnitude or a length of 1. And that makes these unit vectors. The other thing to note, though, is notice that, for example, these vectors are perpendicular or orthogonal. These vectors are orthogonal, and these vectors are orthogonal. In other words, these vectors are also orthogonal to each other. And those are the characteristics for what we're going to talk about in this lesson. So let's jump right into that definition. And the definition for orthogonal and orthonormal sets is this. It says a set S of vectors in an inner product space V is orthogonal when every pair of vectors in S is orthogonal. Okay, so just right off the bat here, coming up here, so we would call this actually an orthogonal basis because all of the vectors are orthogonal or perpendicular to each other. But if we continue, it goes on to say, if in addition, each vector in the set is a unit vector, then S is orthonormal. So orthogonal is one type of basis, but in this case, because both of these hold true, it is both orthogonal and consisting of only unit vectors, that makes this an orthonormal basis. So that is the work that we're going to be doing in this unit, or in this lesson, is talking about these orthogonal and more specifically the orthonormal bases. So mathematically, just symbolically, they kind of talk about what we've got here. So orthogonal just simply means that if we take, again, the inner product of two vectors, it's going to be 0. For our purposes, we're going to stay in the R space, in the n space of R. So we're going to deal with dot product. So if I take the dot product of two vectors and it's 0, that means that those vectors are orthogonal. And that would be true of any two vectors that we pick in that basis. And then orthonormal has that property plus the magnitude or length of every vector in that basis will also be 1. Okay, so if S is a basis, then it has an orthogonal basis or an orthonormal basis. Okay, so yeah, so that just kind of summarizes what we just talked about. All right, so let me do this because I do want to talk about the fact that, as I mentioned, this 1,0,0,0,1,0,0,0,1 is a standard basis, but these orthonormal and orthogonal bases do not have to be the standard basis. They can be non-standard as well. So let me just give you an example of that. So we'll go into 2 dimensions here. We're going to R2. And so we know in R2 that we could have a vector on the x-axis, we could have a vector on the y-axis, and if those have a length of 1, well, clearly then they're perpendicular, so they're orthogonal, they're unit vectors, so that would be an example of an orthonormal basis for R2. Okay, so let me actually write that out. So basically then, the vector space 1, 0, 0, 1, this would be an orthonormal basis. Orthonormal basis for R2. Okay, and in addition to that, we could even say that it's a standard orthonormal basis, right? So standard again because it's the 1, 0, 0, 1. Now, if I took those vectors though, and I rotated them, let's say 45 degrees. So I'm going to take the vector on the x-axis, I'm going to rotate it counterclockwise 45 degrees. And I'm going to take the vector on the y-axis and rotate it 45 degrees. That's going to maintain the orthogonal characteristic. And if I keep the lengths at 1, so this would have, think back to your unit circle in trigonometry. Unit circle has a radius of 1, and one of those ordered pairs at the 45 degree or pi over 4 spot was square root of 2 over 2, square root of 2 over 2. And that would make this negative square root of 2 over 2, square root of 2 over 2. So that those vectors are also, or form a basis that is also orthonormal because they're orthogonal. And each of those vectors, and we could check this mathematically, but each of those vectors has a length or magnitude of 1. So we could say in this case then that the vectors root 2 over 2, root 2 over 2, and negative root 2 over 2, root 2 over 2, that this basically is a non-standard orthonormal basis for R2. Okay, so I just want you to see that again, as we talk about this, there's not just one orthonormal basis for a vector space. In this regard, if you think about this, there are actually infinitely many, because all I have to do is take those 2 vectors and rotate them even the ever so slightest, changing the vectors but still maintaining both properties of orthogonal and being unit vectors. So let's go ahead and do an example then of just showing that a set is an orthonormal basis for, in this case, R3. Now, we could do this for any n space, but to keep the math a little bit lighter, we'll keep it in the R2 and R3, generally speaking. Okay, so in order for this vector or this basis S to be the orthonormal basis for R3, we have to show that again all of the vectors have a magnitude of 1, that they are unit vectors, and that they are orthogonal to each other, that their dot products are 0. So let's start with the latter. Let's start by showing that the dot products are all 0. So we're going to take the dot product of V1 and V2. And in this case, I'm going to actually write this out. These are kind of some crazy numbers. I don't want to get lost in trying to do this in my head. So we've got 1 over the square root of 2 times negative root 2 over 6, and then plus 1 over root 2 times root 2 over 6. And then we're going to have 0 times. I won't write that one out, but our third term would just be 0 times. So that'll be 0. And so notice that the root 2's cancel. And so we have a negative 1 over 6 plus a positive 1 over 6 is 0. Now let's try V1 and V3. Obviously, this is V1, V2, and V3. So V3, our V1, V3 is 1 over root 2 times 2/3 plus 1 over root 2 times negative 2/3. And again, we have 0. Obviously, we can see that these are just opposites of each other, so adding them is also going to give us 0. And then finally, V2, V3. So here we're going to have negative root 2 over 6, root 2 over 6 times 2/3 plus root 2 over 6 times negative 2/3, and then plus 2 root 2 over 3, lost my place there for a minute, over 3 times 1/3. Okay, so we've got negative 2 roots 2 over 18. So negative, what did I say, 2 root 2 over 18. And then minus another 2 root 2 over 18. And plus 2 root 2 over 9. So in that last fraction, if we get a common denominator of 18, we would just have a 4 over 18. So I have negative 2 minus 2 is 0, or excuse me, is negative 4 plus 4 is 0. And so this is also 0. So we know then that because all three pairs of dot products are 0, that these are what we are going to call mutually orthogonal, that each vector is orthogonal to all the others. Okay, so now we need to go through and find their magnitudes. Nobody said this was going to be easy. It's sometimes just kind of tedious work to go through this, but the magnitudes, so for V1, we've got, if I just square that, remember we're doing the square root of each part squared. So if I square that, that's going to be 1/2 plus 1/2 plus 0. So the square root of 1/4, what did I do wrong here? Oh no, I didn't do anything wrong. 1/2, wow, I'm multiplying when I should be adding. 1/2 plus 1/2 is 1. And so square root of 1 is 1. That was close. All right. Next one, V2. Let's hope this one goes a little bit better. All right, V2, we've got negative, well, here, let me just do this. We'll square these in our head. So the top is going to be 2, the bottom is going to be 36. So we've got 2 over 36, positive obviously because we're squaring, plus another 2 over 36. And then in the top squaring, we'd have 4 times 2 is 8 over 9. So again, thinking common denominator, multiplying top and bottom by 4 would give us 32 over 36. So in the numerator, we have 36. The denominator is 36, so that is also 1. And then finally, V3, we'll have 4/9 plus 4/9 plus 1/9, and that is 9/9 or 1. And so because all of the magnitudes are 1, all three of these are unit vectors. And again, because they are mutually orthogonal, because they are unit vectors, that tells us that in this case, I'm going to use that word non-standard, but it's a non-standard orthonormal basis. Orthonormal basis. All right. So that's the idea behind these special bases, that they are mutually orthogonal, that every vector in the basis is orthogonal to every other, and that they are all unit vectors. They all have magnitude 1. All right. So then we just have a theorem and a corollary, and really this is just to kind of expedite the process of finding or knowing if things are orthonormal or not. So our theorem says that if S is an orthogonal set of non-zero vectors in an inner product space V, then S is linearly independent. So basically, if we have a basis and we know that basis is orthogonal, that all of the vectors are orthogonal to each other, then we automatically know that the vector set is linearly independent. The corollary to that, so kind of the follow-up to that, is saying if V is an inner product space of dimension n, then any orthogonal set of n non-zero vectors is a basis for V. So in other words, again, if we've got a vector space V of dimension n, so n space of 2 space, a 3 space, a 4 space, or whatever the case might be, we could be in matrices, we could be in polynomials, it doesn't matter, then any orthogonal set of n non-zero vectors. So notice, and we talked about this also in chapter 4, this idea that if the dimension is n, then the basis is going to have n vectors in it. If there's more, to be linearly independent. If we have more than that, it's not linearly independent. So we're going to have n non-zero vectors, and that is going to be a basis for V. We know automatically that if those n vectors are orthogonal, it is a basis for V. Okay. So I don't really want to say much more than that. We're just going to jump right into an example that's just going to kind of add to what we've been doing here. So we're going to show that the set S below is a basis for R4. Okay. Now, what this does, though, is if we can show that these vectors are all orthogonal to each other, we don't have to then go on and do the rest of this. We just know that it is an orthogonal an orthonormal basis, okay? So let's go ahead and do this. So we're going to just show that these are orthogonal. So I'm going to call this V1, V2, V3, and V4. So V1.V2 looks like we're going to have about 6 of these to do. And I would say just try to be fairly methodic when you do this. So I'm going to take V1 and do the dot product with V2, V3, V4. Then I'll take V2 with V3 and V4, and then V3 with V4. So, and I'm going to just kind of expedite the math here. So for V1, V2, when we multiply those together, we're going to have 2 times 1 is 2, plus 0 minus 2 is 0. The dot product of V1 and V3 is going to be negative 2 plus 0 plus 4. Plus 4 minus 2 is also 0. V1 dot V4 is going to be negative 2 plus 6 minus 2. Whoops, plus 6. Where did that go? Plus 6 minus 2 is 0. And now let's go to V2. V2 dot V3 is negative 1 plus 0 plus 1 is 0. V2.V4 is negative 1 plus 0 plus 1 is also 0. And then finally, V3.V4 is positive 1 plus 0 minus 2 plus 1 is 0. So in this case, then, because of this theorem and corollary that we just talked about, I can immediately jump to the fact that because S is orthogonal, all of those vectors are orthogonal to each other, we know that it is a basis for R4. Now, what this doesn't tell us is that these are orthonormal. Okay, that's not what we're saying here. We're just saying that the process of going through to determine if this is a basis is shortened because of that. We don't have to go through. Think back to chapter 4 and what we had to do to show that a vector space, or that a set was a basis for a vector space. We don't have to go through as much work. In this case, if we can show that they are orthogonal to each other, then they're a basis for that space, for that vector space. But it doesn't mean that they're orthonormal. And in fact, we can see, obviously, these vectors do not have a length of 1. They are not unit vectors, so they wouldn't be orthonormal. All right? Okay. So next one is coordinates relative to an orthonormal basis. Now, we also back in chapter 4 also talked about coordinates relative to a basis. And I'm going to kind of bring you back and remind you of that just a little bit when we do this. But basically what this is now is specifically for an orthonormal basis. So if B is an orthonormal basis for an inner product space V, then the coordinate representation of a vector W relative to B is given by the following. Okay, so back in 4.7, if you wanted to refer back to that to remind yourself of what we did here, we found coefficients for the linear combinations. Okay, so we found coefficients for linear combos. I'm just going to say it that way, for linear combos. And the process that we had to go through was fairly involved. We had to basically set up a system of equations. We solved the system of equations, and then we used that system to basically come up with these coefficients. So it was a fairly lengthy, fairly involved process in chapter 4 to find the coefficients for a linear combination. What this is doing, by the way, all this is doing is if I have a vector W, right? So W is a vector. This whole thing is just the linear combination that gives us W. That's all we're doing here. And what we're doing is talking about the coordinate representation is what are the scalars that we're using to multiply the vectors to get that vector W, to create that linear combination. So we did that back in chapter 4, fairly lengthy process. And now what we're going to do is again, because of what we're learning in this section, we can kind of streamline the process a bit. Okay. So basically what this is doing, and I'm going to go to R2 for this example again. So let's suppose, for example, I have a vector, and I'm just going to call it vector W. I'm going to put this up into the second quadrant here. Okay, so this is my vector W. And we know, for example, that I'm going to create unit vectors I and J. This is the unit vector I, this is the unit vector J. So this goes to 1, this goes to 1. What we're in essence doing is we are figuring out, in R2 at least, what we'd be figuring out is how to represent W as the sum of two other vectors. Okay, so I'm looking at how do I create W as a linear combination of two other vectors, W1 and W2 we'll call them. And so in this case, what I could do is project W onto I and create what I'm going to call W1. That would be our W1, which is the projection of W onto I. And then I'm going to create another vector, and I'm going to call that another projection, and we're going to call that W2, which is the projection of W onto J. So I think clearly we can see that W can be represented by the addition or the sum of those two vectors, W1 and W2. Well, another way to think about the projection of W onto J, or let me start with I onto I, is that W1 is very simply I times a constant, a scalar. And likewise, W2 is just a scalar times J. Okay, so then I can think of W1 plus W2 as being just a constant times I plus a constant times J, which is exactly what this formula up above is doing. This formula is basically saying that the product, or the inner product of W and V1, the inner product of W and V2, the inner product of W and Vn are giving us those constants or those scalars. Remember, an inner product is always a scalar, and then V1, V2, and so on just represent, in this case, what I'm using as I and J for this example. Okay, so we can think of this as just, in our terms, being the dot product of W and I times I plus the dot product of W and J times J. Where again, the dot product of W and I would just be C1. The dot product of the W and J would be C2. Okay, so that's kind of, in theory, what we're doing here to find the coordinate representation of that linear combination. If that doesn't make sense, let's jump into an example and use a concrete idea to hopefully kind of drive this home. So our next example says find the coordinate matrix of W equals 5, negative 5, 2 relative to the orthonormal basis B for R3 below. So again, B is our basis, so these three vectors make up our basis, and we basically want to find a linear combination that is going to give us vector W. Now specifically what we're looking for is we're looking for those scalars that we would multiply each of these three vectors by in order to create that linear combination. That's what we're doing here, okay? So what we're going to do, again, just thinking of this formula above, we're going to take the dot product of W and V1. So I'm going to call this V1. Here, I'll write it below V1, V2, V3. Now, I don't need to necessarily worry about multiplying by these vectors up in the equation. I don't need to multiply those because I don't need the actual vectors. I just need the coefficients or the scalars in front of them. So I just really need the W, the product, dot product of WV1, the dot product of WV2, and the dot product of WV3. So with W dot V1, that is going to be 5 times 3/5 is 3. Negative 5 times 4/5 is a negative 4. And then 0. So that is going to be negative 1. And then the dot product of V2, or W and V2, is going to be a negative 4. And then negative 5 times 3/5 is negative 3. And then another 0 is negative 7. And then the dot product of W and V3 is going to be 0, 0, and 2. So just 2. Okay. So in this case then, we would say that the coordinate matrix, that's what we're looking for, is a coordinate matrix relative to B is going to be, and this is just this notation for this again, is going to be the coefficients or the scalars 1, negative 7, 2. Now, this is actually technically a column matrix. So I'm going to just put a little T there to show that we actually want the transpose of that. We actually want that as a column, one column matrix, not a row matrix. But what this is saying then is that if you take negative 1 times V1 plus negative 7 times V2 plus 2 times V3, that will give you the vector W. So these are the scalars that we would need to create the linear combination that produces W. Okay. So all this is doing is exactly what we did in chapter 4, finding those coefficients, finding those scalars, except in a much more streamlined process because we don't have to set up the system of equations that we then have to try and solve and et cetera, et cetera. All we have to do is really just find these dot products and that's it, and you're done. All right, so the last thing we're going to talk about is this thing called the Gram-Schmidt orthonormalization process. Oftentimes we'll just refer to it as the Gram-Schmidt process, okay? And what this is this is how we take a basis and we turn it into an orthonormal basis. So basically, if you look at the theorem here, we've got 3 steps that we're going to go through. The first is that we simply have to define what the basis for the inner product space is. And that basis does not need to be orthogonal, nor does it need to be orthonormal, because that's what we're going to do. That's the whole point of this, is to make it orthonormal. Then we're going to take that basis. So it does have to be a basis for the vector space. That's kind of the critical part here. It is a basis already. We're going to take that basis and we're simply going to make it an orthogonal basis. So we're going to rotate those vectors, in essence, to or create their projections to create a basis of orthogonal vectors. And then the last step is to normalize them, to put them into a magnitude of 1 to create them as, or to change them or transform them into unit vectors. So I'm not going to go into a lot of detail with this next part here, because this is actually the theorem just showing how we would go through and actually do the work of creating creating the orthonormal basis. I do want to point out, however, just, so step 1, we start with a basis, right? So that's our basis. Step 2, we're going to now find the orthogonal bases, okay? Or the orthogonal vectors. So notice we just start by just saying that W1 equals V1, okay? So we're just doing this. We're saying V1 is W1. And then to get the remaining, because now from that starting vector, now we want to create all the other vectors that are orthogonal to it. We're going to do that by projecting. So if you look at the next formula, W2 equals, this whole thing right here is a projection. This is a projection of V1 on, or excuse me, V2 onto V1. So we start with a vector V1, and then we're going to project onto V1 to create an orthogonal vector. And then we do that again if we're in the third space. We do it again if we're in the fourth space. And we keep going until we have a set of completely orthogonal vectors. Once we've done that, then in step 3, we just find the unit vectors. Okay, so this is how we convert to unit vectors. And we've done this before, where we just take the vector and we divide it by the magnitude, and that's going to convert it to a unit vector. All right, so with that, let's go ahead and I think before I get into an example, let me show you this pictorially. I've got a little room here at the bottom. Let me actually draw a picture and try to explain, because this might be a little confusing on the onset, and I want to make sure it's understandable. So let's start with 2 vectors. We're gonna again do this in R2. So let's start with a vector V1 and a vector V2. So the idea is, again, I'm going to pick a vector, and that's going to be my starting point. So I'm going to pick V1, for example, and that's just going to be W1. From that vector, we're now going to start creating these other vectors. So I'm going to project W2 onto V2 onto V1 or W1. So I'm going to project this vector, and I'm going to create this, which is the projection of V2 onto V1. Okay, now that vector so the vector I'm looking for is not the projection. Notice that what I'm looking for is, when I'm looking for the next vector, that second vector, I'm taking V2 minus the projection. So I'm taking V2, here's V2 minus the projection that I just created. Well, that is this vector right here. That is this vector. In fact, let me change this color to green here so we can see that better. This is the vector that we're actually looking for. And if I translate that over and draw that vector right here, we can very clearly see then that that is going to be perpendicular to V1 or W1. So this is now W2. And like I said, if we were to keep going, if we were in 3 dimensions, we'd do this again for a third dimension, and we just keep adding on. So now you're taking V3, but now you're finding basically having to subtract 2 projections because we're in 3 dimensions. In 4, you'd end up having to subtract 3 dimensions, 4 dimensions, 5 dimensions, and so on. Okay, but that's the idea. Is we're actually creating out of V2, we're actually creating out of this vector and the projection this orthogonal vector. Okay. So let's go ahead and let's do an example of this. And we're going to do two examples. We'll do one in R2, and then we'll finish this lesson with doing this in R3. So very simply says apply the Gram-Schmidt process to the basis B for R2 below. So again, step one, we have to have a basis. So we've got our basis 1, 1, 0, 1. And in this case then, well, we're going to start, if I call this V1, call this V2, we're going to start by just saying that W1 is going to equal V1 or the vector 1, 1. Then I want to now create W2. So to create W2, what we're going to do is we're going to basically run this formula up here. So I need to take V2 minus the projection of V2 onto V1. Okay. So in other words, W2 is V2 minus the dot product of V2 and W1 divided by the dot product of W1 and W1. And then we're going to multiply that by the vector W1. So in this case, V2 is 1, 2, is 1, 1. And then minus the dot product of V2 and W1, which is also V1, is 0 plus 1, or 1. And then on the bottom, the dot product of W1 and W1 is 1 plus 1, or 2. And we're multiplying that by W1, which is 1, 1. And I think I made a mistake here. This first vector I messed up on. That shouldn't be 1, 1. That should be V2. That should be 0, 1. Okay. So we've got 0 minus 1/2 is negative 1/2. And then 1 minus 1/2 is a positive 1/2. Okay. So in this case, we're actually just about there. But these two vectors now, this vector and this vector, these form our orthogonal basis for R2. Okay. Now we're not done yet. That's the orthogonal basis. So those two vectors, and if we graph this, we can see this, that if I graph this 1, 1 is here, negative 1, negative 1/2, negative 1/2 is here, those are perpendicular. They're orthogonal. Now we need to keep going though, and now we need to find the unit vector. So we're going to convert these now into unit vectors. So U1 is going to be W1 divided by the magnitude of W1. And in other words, if you want to think of it this way, like 1 over the magnitude of W1 times W1, if that helps to think of it that way. So 1 divided by the magnitude of W1 is square root of 1 plus 1, or square root of 2. And then times the vector itself, 1, 1, which is going to be 1 over the square root of 2, 1 over the square root of 2, or if you prefer to rationalize, get the square roots out of the denominators, root 2 over 2, root 2 over 2. And then U2, we're doing the same thing. We're going to take the magnitude of W2 now, divided by, or excuse me, take the vector W2, divided by the magnitude of W2. And that is going to give us 1 divided by, magnitude is 1/4 plus 1/4 is 1 over the square root of 2 times the vector negative 1/2, 1/2, which is the same as square root of 2 times negative 1/2, 1/2, or negative root 2 over 2, root 2 over 2. All right, so that means that then that the set negative root 2 over 2, root 2 over 2, and positive root 2 over 2, root 2 over 2 is an orthonormal basis. Orthonormal orthonormal basis for R2. All right. So going back to our picture above, and let me go back to a different color now. So basically what we've done is, in this case, we actually extended out, or actually we brought back in this point and this point, and basically we just multiplied by a scalar to create vectors now that each have a length of 1, are obviously still perpendicular to each other, so they're perpendicular, they're unit vectors, and therefore they create an orthonormal basis. All right, last example for this lesson, we are going to do the same thing, but now we are in R3. So same idea. We've got V1, V2, V3. And so we're going to start by letting W just equal V1, which is the vector 1, 1, 0. W2 is going to be V2 minus the dot product of V2 and W1 divided by the dot product of W1 and W1 times the vector W1. So V2 is 1, 2, 0 minus the dot product of V2 and W1 is going to be 1 plus 2 plus 0 is 3. The dot product of W1 and W1 is 1 plus 1 or 2, and that gets multiplied by W1, which is 1, 1, 0. So we'd have 1 minus 3 halves is negative 1 half. 2 minus 3 halves is a positive 1 half. And then 0 minus 0 is 0. All right, now we have to take this one more step, though, because we're in 3 dimensions, so we need to find a W3. And W3, so coming back to our formula above, here's the formula that we're using for W3. So now we're going to take V3 and we're going to subtract now the projection of V3 onto W1 and so on and so forth. Okay. So in this case now, we've got V3. I'm just going to write out this formula so you've got it down here as well. We're going to take the dot product of V3 and W1 divided by the dot product of W1 and W1 times W1. But again, we need to subtract another one, and this time it's going to be V3 and W2. So the dot product of V3 and W2 divided by the dot product of W2 and W2 times W2. Okay, so in this one now, V3 is 0, 1, 2 minus the dot product of V3 and W1 is going to be 0 plus 1 plus 0 is just 1. The dot product of W1 with itself is 1 and 1 is 2. And times W1 is 1, 1, 0. And then minus, and now we're going to do the dot product of V3 and W2. V3 and W2 is going to be 0, 1 half, and 0. So we have a 1 half in the numerator. And then W2 with itself is going to be a 1/4, and a 1/4 is a 1 half. So actually that coefficient of that scalar is just going to be 1. And we're multiplying that by W2, which is negative 1 half, 1 half, 0. And that'll just give us that excuse me. And that'll give me the, actually, let me do this down at the row below. So we've got 0, 1, 2 minus 1 half, 1, actually, let me do this. I'm going to do plus a negative 1 half. I think that'll be easier. I won't get messed up on the negatives. So that just makes those negative 1 halves, and then plus a positive 1 half, a negative 1 half, and a 0. You could either subtract or add. I prefer adding in this situation. It's just, for me, it makes it a little bit easier that I don't get confused. So adding, I'm going to have a negative 1 half and a 1 half. That's actually 0. And then we've got 1, a negative half, and a negative half. That is also 0. And then 2 plus 0 plus 0 is just 2. Okay, so That was a lot. Let's pause for a minute here. So this vector, and this vector, these are the orthogonal vectors, okay? You can see that as we get going here, if we were to do like, imagine doing a 5 space in R, the work involved to create that fifth vector, where you're having to do, you're subtracting multiple vectors by times their scalars and so on. It can be a lot of work. And at that point, honestly, that's where we introduce technology, and we just start doing a lot of this with technology. Beyond, even R3 is probably a little bit of a stretch, but I certainly wouldn't even want to do R4 by hand. I would turn to technology to do that. All right, so let's keep going then. And now we have to convert these into unit vectors. So U1 is going to be, and I'm not going to write down the formulas first, we're just going to jump right in, but U1, so we need the magnitude of V1, or excuse me, of W1. So square root of 1 plus 1 is the square root of 2, so 1 over the square root of 2 times 1, 1, 0 is going to be 1 over the square root of 2, 1 over the square root of 2, 0. Or again, if you prefer, root 2 over 2, root 2 over 2, and 0. U2 is going to be, let's see, we've got 1/4 plus 1/4 is 1/2. So we have 1 over root 2 times the vector negative 1/2, 1/2, 0. So this whole thing, right, if we simplify this is just the square root of 2. So we're just multiplying by the square root of 2. So that gives us negative root 2 over 2, root 2 over 2, and 0. And then finally U3 is going to be 0, 0, and 4. So that's just 1 over 2 times 0, 0, 2 is the vector 0, 0, 1. So these three vectors right here, I'm not going to write this out formally, but these three vectors create the orthonormal basis for R3. Now again, this is not necessarily the only, in fact, this isn't the only orthonormal basis in R3. It just is one orthonormal basis in R3. And again, we could show that they are perpendicular. We could show that they are unit vectors, but the process creates that. So that is it for this lesson. Wow, that was a lot. I actually feel tired after that one. But make sure that you just know how to, find orthogonal vectors, how to show that they are orthogonal, how to show that they are orthonormal, that they've got that unit vector condition met, and then know how to just go from any basis into the orthonormal basis using this Gram-Schmidt process. All right, that is all. I am spent. You might be too. So we're going to end it here, and I'll see you in the next lesson.